Um, Today is the last section of new material before the exam. This will be section 10.1. If you want to just write on that side. This is section 10.1. And I mentioned before that that's kind of an odd place to stop to give a test after one section in a new chapter, but that's just the way it worked out so that the test fell on the day I wanted it to fall before the holiday. Right? That way you can have the test before you go on break and not have to spend your break studying. So, most people think that's a good thing. Some people don't because they want the break to study, but I played the majority. So, here we go. Section 10.1. Before I do that, are there any questions about section, about anything in chapter 9 that we just finished? Any remaining questions there? You have homework tonight over 9.5. No questions? All right. Then let's jump into 10. Chapter 10 starts into two sample problems. The way that he sets the book up is chapter 8 is confidence intervals for one sample problems. Chapter 9 is hypothesis tests for one sample problems. And then chapter 10 are two sample problems, both confidence intervals and hypothesis tests mixed together. So we'll get both of those things today for two sample proportions problems. Now remember, I've been saying for a while that I recommend on your cheat sheet that you bring in that you have it separated out for means problems and proportions problems. And all the formulas that go with means are in that section, and all the formulas that go with proportions are in those sections. And I've always been telling you, when you read a new problem, big long paragraph that you're supposed to read, first thing you should do is decide, okay, what kind of a problem am I dealing with here? The first question you ask yourself is what? Is it means or is it proportions? Okay? Now we're going to add a second question to that. Is it a one sample problem or a two sample problem? Okay? So if it's a two sample problem for this next test, then you know it's a proportions problem because we're not going to get to the next section, which is means two sample, but we will as soon as the exam's over. When you talk about two samples, there are two ways that can happen. So after this exam, we're actually going to add another question. Are those two samples dependent samples or independent samples? So let's talk a little bit about what that is. Independent samples means the same thing that it meant, basically the same thing that it meant when we used that word independent when we talked about probability of events. Two events were independent if knowledge of what happens in the first event does not change anything or knowledge about what will happen in the second event, particularly the probability. Same thing is true for samples. If I have two groups of people that I want to estimate proportions from, then I need to know, are those two groups independent? Okay? So generally what that means is they're independent if they're just completely different samples of people, different people in the two groups. Okay? So maybe I have a sample of males and a sample of females. Well, those two groups would be generally considered to be independent. If I know how, the number of successes among the males, maybe it's people who answer yes to a certain question, that really doesn't give me any information about the percentage of yeses I expect to get in the female group. Right? So they would be independent samples. An example where they would not be independent would be if I use the same people twice. So suppose when you first get to Washburn as a freshman, I give a survey and I ask a few questions. Right? And on question number 3, I'm estimating the proportion of people who say yes to question number 3. Then I give the same survey when they graduate to the same people. Those are dependent samples. because when you ask the same person the same question twice, the answer they gave the second time is probably going to be more likely to be the same as what it was the first time. So it changes your idea of probability there. Okay? So essentially, independent samples, I'll say usually means different people. It doesn't necessarily always mean that, so you have to give it a little bit of thought. For instance, suppose I say, well, I got a sample of males and I got a sample of females. Oh, by the way, they're all married couples. I say, oh, those aren't dependent samples then. They're not independent samples, they are dependent. Because husbands and wives sometimes have similar opinions on things. Right? So if I happen to get more Republican males, I probably have more Republican females too. Right? So those might be dependent, even though they're different people. But if there's any kind of a relationship between the two samples, we would say they're dependent. So what we're going to do in section 10.1 requires independent samples. Right? So remember, any statistical procedure, there are assumptions that have to be met. What's the first assumption? Random samples. Right? Well, now we have two samples we're dealing with. So we say both samples have to be random, and for 10.1, those samples must not only be random, but they must also be independent. So independent random samples. That's assumption number one. What's assumption number two always? What's that?
Sample size?
Sample size requirement, right? We're going to be doing proportions in section 10.1. So do you remember what the sample size requirement was for proportions problems? 15 successes, 15 failures. Well, now I got two samples. So I say I need 15 successes and 15 failures in both of those samples. Okay? So that's the assumption. Let me write that here, I guess. Assumptions. Both samples are random and they are independent. I'll abbreviate independent. And then, so that's number one. Number two, greater than or equal to 15 successes and greater than or equal to 15 failures in each sample. So it's not fair to say, well, I had 8 successes in sample 1 and I had 9 successes in sample 2, therefore I met the 15. It has to be in both. You have to have 15 in the first one and 15 in the second. Okay? So this applies to both confidence intervals and hypothesis testing. Okay? Now, let's talk about confidence intervals. If I have a 2-sample proportions problem and I want a confidence interval, we need to build the formula for computing, that's not good, for computing confidence interval. Now, in general, what do all confidence intervals look like?
Plus or minus a margin of error.
Good. Point estimate plus or minus a margin of error. So now all we have to do is figure out, well, what is our point estimate and what is our margin of error? And remember, that changes depending on whether it's a means problem or a proportions problem, 1 sample, 2 sample, those things are going to change. But in general, it always looks like that. This is going to end up being a fun day with a new marker. Okay. Well, to talk about what our point estimate is going to be, we have to think about, okay, this is a two-sample proportions problem. So what exactly is it that I'm trying to estimate? Well, I'm trying to estimate proportions, but if I'm interested in two different proportions, mainly what we're interested in is, are they different or are they the same? Do males answer this question differently than females? Or do smokers exercise at a different rate than non-smokers? Questions like that. So we want to compare these two proportions. So when we have two samples, I can divide them into sample 1 and sample 2. And a lot of times I'll call that group instead of sample. So group 1, group 2. When we have one sample proportions problems, we define X and N and P hat. Remember those? What is X? Number of successes, right? So X is number of successes. N is sample size. And P hat is point estimate of the proportion. So it's the sample proportion. And how's it computed? X over N. Good. X over N. Well, now I've got two samples. So in order to keep it straight of which sample I'm talking about, what would be a handy thing to do? Subscripts. Good. X sub 1, N sub 1, P hat sub 1. And P hat sub 1 is X sub 1 over N sub 1. So then in my second sample, I get all those same things. X2, N2, and P hat 2. Now for hypothesis testing, because we're doing both today, remember? If I want to do a test about the proportions from two samples, I already said what I'm interested in is whether or not those two samples, or I'm sorry, those two proportions are the same. So what would the null hypothesis be? That they are the same, right? Null means none, no difference. So you can write that two ways. You can write P1 equal P2. Notice it does not have a hat on it. The null hypothesis and the alternative hypothesis, you never put your sample values in there. It's always the population parameters that go in there. Right? Now, algebraically, that's equivalent to saying this. Right? Just subtract P2 from both sides. But I like that second way of writing it because that's the one that says there's no difference. The difference is 0. This one says they are the same, which is fine. But this is what we think of when we do confidence intervals. We put a confidence interval on this difference. Okay? So, back to confidence intervals. Point estimate. What's the point estimate of that difference? What'd you say?
That P1 minus P2?
Okay, P1 minus P2, is that a point estimate? Not quite. You gave me population parameters.
Oh, P hat?
P hat. Sample estimates. Whenever I ask that question, what's the point estimate of this? Your answer should always be, it's that thing from the sample one of those, right? So what's the point estimate of this difference? It's the sample difference. Okay? So now I've got my point estimate, I need to talk about the margin of error. Now the margin of error always has two parts to it. What goes into computing a margin of error? The standard error of the point estimate. And you don't remember the other one. Critical value. That's right, critical value. Right? Now for proportions problems, what is that critical value? Z or T? It's a z. So this will be a z critical value. Remember that's 1.96 or 1.645 depending on what your confidence level is. Then we need the standard error of p hat 1 minus p hat 2. So that guy is a little bit tricky. Now I'll warn you right off the bat that the standard error that is computed for a confidence interval is slightly different than it is for a hypothesis test. We had the same difference when we did one sample problems. Remember, for a confidence interval, the standard error had p hats in it. But for a hypothesis test, it didn't have p hat, it had the hypothesized p. Because you're assuming the null is true, therefore you know what the true proportion is, so you use it in your standard error. Okay. It's a little more tricky with two sample problems, but not horribly. Remind me what the standard error of p1 hat is. Not the difference between two proportions, but just for one proportion. Square root of p hat times 1 minus p hat, and notice I'm putting the subscript on there this time, divided by n1, right? So I'm putting the subscripts on there because I'm specific about which sample I'm talking about. So if I want the standard error of p hat 2, then I just put the sub 2's in there. But what I really want is I want the standard error of the difference. Now, here a lot of times people, as kind of their first thought of what would that standard error be, well, it's just going to be the difference in the two standard errors. Standard error of p hat 1 minus the standard error of p hat 2. It doesn't work that way. Because if you think about it, oh yeah, I guess that could lead to zero standard error, right? What if the two standard errors happen to be the same in the two samples? Then you get a 0. You say, hey, I can estimate the difference with no error at all. Or even worse, what if the standard error for the second sample happened to be bigger than the standard error for the second or for the first sample? Now you get a negative. You can't have negative standard error. That doesn't make any sense. So the way it works, and I'm not going to derive this algebraically, although it's not a real difficult derivation. It's just not something that I'll make you do, so I'm not going to waste the class time to do it. Basically, you square the two standard errors. So if I square this, all I do is remove the square root. And then I do the same thing for the one for p hat 2. I add them together, and then I put the square root back on. So here's what it looks like after all that. p1 hat times 1 minus p1 hat divided by n1 plus p2 hat 1 minus p2 hat all over n2. What's that?
I'm confused on the beginning of the problem, standard error p1 minus p2.
Yeah, and that's what I said. The first attempt, people tend to want to subtract them here. But you don't subtract them because if this number turned out to be bigger than this number, you get a negative, and you get a negative under square root, all heck breaks loose, right? So you add them, and it's a statistical theory thing, but if you think about it, I've got two random variables in here, so I need roughly twice as much variability. So I got two things that are random instead of one thing that's random. So the standard error actually goes up, even when you take a difference. Okay? It's interestingly, the standard error of the sum of these two is exactly the same. The standard error, if I added two proportions together, the standard error would be the same. But anyway, that's news for another day. Okay, so if I take that thing and stick it in here, how's that? Then I have the formula for computing the confidence interval by hand. Right? And Chelsea went, I don't want to do that. What do you want to do?
Calculator?
Grabs her calculator, yeah. Now look in your calculator and see if you can figure out where you would go to do a confidence interval for the difference in two proportions.
Two and Z.
Not quite. It's, you need the prop in there because this is a proportional prop. So it's a 2 prop Z int, and this over here, the hypothesis test, will be 2 prop Z test. Okay? So, on the calculator, so on the TI 83 or 84, we're going to use 2 prop Z int for intervals, or 2 prop Z test for hypothesis test. Okay? But, like I always do in this class, I want to do one of these by hand the long way, and then we'll confirm that, oh, we get the same thing a whole lot easier if we just use our calculator. And I want to mention that I'm still getting, not a lot, but a few ask my instructor questions when people are doing their homework, and they say, here's how I did it, and I'll write back, boy, you did that the hard way. Use T-interval. You were one of them. I hate to single you out. But, you know, she was using the formula. And then something was going wrong in the formula. If you just use the thing on the calculator, then you'll get the interval right. Now, the danger with that is you learn to rely on this calculator and you have no idea what it's doing. That's why I like to do one by hand so you understand, well, what is the calculator doing? Because some of the online homework problems, and probably at least one of my test questions, I might ask, what's the standard error? And the calculator doesn't do that. It just gives you the interval. So you don't know what standard error it used. Okay? So it may ask that, or it may ask, what's the test statistic? Well, it'll give you the test statistic, but it won't show you how to compute that by hand. It won't show you the standard error that goes into that test statistic and things like that. Right? If I could also ask you, what's the margin of error that this confidence interval used? Right? So you need to be able to work with the formula to get those things that the calculator isn't automatically going to give you. But you can always check your work with the calculator. Right? When you're doing the online homework, if it says compute the 95% confidence interval, go right to the 1 prop Z int and do it there. Don't risk making round off errors and things like that doing it the wrong way. Okay? But let's do it first. Let me get an example problem up here. And this problem, I guess I can't. I was hoping that would be up on the top half. This data is from your data that you guys collected for me. So I have 385 observations, cross-tabulated by whether or not people smoke and whether or not they exercise. Okay? Do you remember this, seeing this table back in chapter 3? We did contingency tables. So what I have, what I'm going to do is I'm going to put this up and then I'm going to collect the numbers that I need off of that table. Okay? So I'm going to work my arm up and down as I write things down. So here we go. What I'm going to do is I'm going to treat my two groups as smokers and non-smokers. So those are my two groups. And what I'm going to count as a success is whether or not they exercise. All right? So I want the proportion who exercise among non-smokers and the proportion who exercise among smokers. Way back when, what did we call those kind of proportions? Conditional proportions. So what I'm doing is I'm doing a test for the difference in two conditional proportions. We're doing a confidence interval. Okay? So, what is my N1? good point. We've got to decide which one we call group 1 and which one we call group 2. And if we pick wrong, we get it all wrong, don't we? Does it matter? No, it doesn't matter which one you call group 1 and group 2. But once you pick it, you have to be consistent. You can't in one place say it's group 1 and in another place switch it, because your subtractions will all be off. If you pick group 1 different than your neighbor picks it, the only difference you'll have is that you might get a negative difference in proportion and they get a positive, but you'll get the same value. One will be positive, one will be negative. And what happens with the ends of the confidence interval, same thing. The ends switch places and switch signs. So, let's call the top row, which is non-smokers, so this is an N for smoke. Non-smokers, what's my N1? How many non-smokers do we have? 322. Okay, what's X1? Amy, what's X1? Number of successes among the non-smokers. 217, very good. Because I said we're going to count the people who exercise. That's a success. So I got 217 successes and 105 failures. Morgan?
I thought it was X. But it,
Oh, I did. You're right. It should be up here. 217. I was just seeing if you were paying attention. You were. Nobody else was, but you were. Just kidding. Okay? So now what is P1 hat? Okay? 217 divided by 322, which is, as a decimal, 0.6739. Okay? Now, let me pull this down just a little bit. Give me the same values for my second sample, for smokers. 63 total, so that's N2. X2 is, what'd you say? 20, good. There were 20 people who said yes, they exercised, among the ones that said they were smokers. So my P hat is 20 over 63, which is 0.3175. Now at this point, sometimes people say, well, why do I need some fancy schmancy statistical test to tell me if those are different? They're different. One is 67%. The other one is 32%. That's a huge difference. It just happened to work out that about 2/3 of the non-smokers exercise and about 1/3 of the smokers exercise. So a very big difference. So yeah, we know that if we do a statistical test of this, it's going to be significant. There's a significant difference in those two proportions. But just humor me. Let's do it. So here we go. I want to do this by hand. So we need to compute P1 hat minus P2 hat. That's 0.6739 minus 3175. Now I'm going to go ahead and write it out like that, but then you tell me what the number is. So that's 0.3564. Like that. Okay? And then plus or minus Z critical value. Well, I want to do a 95% confidence interval, so what would my critical value be? 1.96. Good. Okay, and now standard error. Ooh, that's nasty. We got to do that one. So let's fill in the numbers. Oh, no. My arm's going to get tired. I have to press so hard on this board. Okay, so here's what you're going to enter in your calculator. And these calculators that you have are sophisticated enough, you can actually enter a big square root and then put all this in there using parentheses where you need to, and close off the square root parentheses after the end of it, and it'll work. All right, so here we go. P1 hat is 0.6739 times 1 minus 0.6739, divide by the sample size in that group, which was 322, plus 3.3175 times 1 minus 0.3175 divided by the sample size in that group, which was 63. So that square root goes across the whole thing. So when you hit the square root button on your calculator, second function square root, it'll open a parenthesis. So after you get past all of this, using these parentheses, put another parenthesis to close that square root. 0.0642. That looks right. Okay, so here we go. We're going to put that number in over here. .0642. So now I have that difference, and now I have my margin of error. Multiply that number, I forgot the 2, by 1.96 to give me the margin of error. 0.1258. If anybody disagrees with him, sing out.
So I multiplied it against the whole number, not just the.
Yeah, and that's actually what you should do. Don't round off at intermediate steps any more than you have to, or you end up with a compounded round-off error at the end. But keeping 4 decimal places here is probably enough, but you wouldn't want to round to 2 places each of those and then use them in there. Your standard error would be off a fair amount. Okay? All right, so now let's convert that into an interval notation. Do the subtraction. 0.3564 minus 0.1258, and that's the lower bound of the interval. Delaney, you got it?
0.2306.
0.2306. And then the upper bound, you use a plus sign. Eddie, do you have that? Nope.
0.8655 or 56.
0.8656,
Yes.
like that.
I had 0.4822.
Oops. I was just going to say, boy, that's a wide interval. Because it goes from 23 to 86. Which is exactly what I want you to do when you write down answers on a test. We all make mistakes. Some of us catch them. Right? So you look at that and go, well, I've got a fairly big sample here. I wasn't expecting a confidence interval that wide. So then you go back and find your mistake. And what is it now, Chelsea?
0.4822.
4822. Does everybody else think that sounds better? Okay. It's still a fairly wide confidence interval, but I have one group that is only 63 people in it. So. All right, now, on the exam and on the homework, you don't only get to compute the confidence interval, but you also get to interpret it. So what is that? What is that? 0.23 what? Remember, interpretation of a confidence interval always starts like this. We are 95% confident of something. What is it that we're confident of in this case? No, I want you to use the numbers in here. Right? That is true. I could make that statement, but that the true proportion of non-smokers who exercise is in that interval?
Compared to that don't.
Yeah, you haven't talked about smokers, right? And I used both here. So what is it that's in there?
Difference.
The difference.
The true proportion
The
of the difference of.
The true difference in the proportion of smokers who exercise and non-smokers who exercise is in that interval. So when I am grading your test, I'm going to skim what you wrote, and I'm looking for the word difference. I'm 95% confident that the true difference in proportions is in that interval. So what I'm saying is there's anywhere between a 23% difference between smokers and non-smokers, maybe as much as a 48% difference between smokers and non-smokers. Okay? So that's the interpretation of the interval in a two-sample type of problem. Okay, now you get to do it the fun way. Grab your calculator. Push the stat button, go over to tests, and go down to 2 prop z int, which we talked about a little while ago. Okay, so 2 prop z int, and hit enter. And don't forget when you make your cheat sheet out to put those things on the cheat sheet. If it is a 2-sample proportions confidence interval, then I'm going to use 2 prop z int. Right? Have it on the cheat sheet so you're not just grabbing the wrong one by accident. So it asks for 4 things. And those are the 4 things that we collected. Top 4 are there. Right? So just enter all of those as shown. 217 and 322 for the first sample. And then 20 and 63 for the second sample. Set the confidence level at 95% and press calculate. And we get 0.23062 and 424822. Now we've got a slight round off error there at the 4th decimal place, right? That one would round in 4 places to 2.3, and we've got 2.2, but you know, you're to the nearest 100th of a percent, that's pretty good. Why is there a slight round off error? Well, because we rounded at these intermediate steps to 4 places, right? The calculator's keeping probably 16 decimal places of accuracy at every step, so it's going to be more accurate. So this is the one that's more accurate. But that's pretty good. Okay? Any questions on how to do that? So if I ask you for what is the standard error of the difference in these 2 proportions, then you're going to go to this formula and plug in the numbers. Okay? If I ask you what's the confidence interval, you're going to go to 2 prop z int, just enter the data, and go from there. Okay? Now hypothesis test. I already wrote down here what the null and alternative, no I didn't either, I just did the null. There's 2 forms that the null can take on. I like this one because it's in the same form that my confidence interval's in. So if I use this confidence interval to test that hypothesis, what would your conclusion be? Would I reject the null, or do I not have enough evidence to reject the null? Okay, say it loud.
So you'd reject the null because they don't equal 0.
You would reject the null hypothesis because the confidence interval tells me what values of the difference are plausible, and 0 for the difference is not in the interval. So 0 is not plausible. So I'm going to reject the null in favor of the alternative. Now the alternative also can be written either way. The alternative is P1 not equal P2, or less than or greater than, if it's a one-tailed test. Or you can do that subtraction and say P1 minus P2 is not equal to 0. And again, I like that because that I can do straight with the confidence. And then a less than or greater than there. Okay? All right, let's check our assumptions. We forgot to do that before we did our confidence interval, but let's do this same data using a hypothesis test, check the assumptions. What'd you say?
It wasn't random.
It was not random. Neither of the samples, the smokers or the non-smokers, were random samples. So we failed that first assumption. What about the second assumption? What is the second assumption? Which I've erased.
15 and
15 successes and 15 failures in both of the samples. In the first sample, I had 217 successes and the rest out of 322, which I think was 105 failures. So no problem. What about this one? We had 20 successes, so it is at least 15. It's not a whole lot more than 15, but it is 15, greater than 15. And then the rest, which would be 43 failures. So we did meet that. So we did not meet the random sample assumption, but we met the sample size assumption. So,
Was it independent as well?
good question. Would they be independent? Yeah, they would be because they're different people. The smoker, you can't be both a smoker and a non-smoker, so you know they're different people in those two samples. There might be a little bit of question about that because of the way you guys collected your samples is, you know, that they may have been family members or whatever, and you know, a husband and wife or anything like that. But you know, we already didn't meet the random assumption, so if we're going to hand wave that off, we'll hand wave off the independence too. Okay, so the 5 steps of a confidence interval. The first one we've done, and that is check the assumptions. The second one is to write out the hypotheses, and for a 2-sample problem for proportions, it is almost always this. You're just almost always checking, are they the same versus not the same? Rarely will they ever say, test to see if the difference is bigger than 60% or something like that. It'll always just test to see if there is a difference. Or they might say, test to see if smokers are lower than non-smokers. And then what kind of an alternative would that be? Which one of these symbols would I use if I worded it that way? Test to see if smokers exercise at a lower proportion than non-smokers. I'd use it. Which would I use? Which did I call P1? Called that non-smokers. You got to be careful there. Remember I said it doesn't matter which one you call 1 or 2, but once you pick them, now you got to be consistent. You have to, you know, they might use the word lower, and you're thinking, okay, less than symbol, but wait, I numbered my groups the other way. So smokers being lower means this one's lower, so it's that symbol. That non-smokers is greater than smokers. So be a little bit careful with that. Okay, what is the third step? My arm is tired. Okay, step number 3 is determine the correct procedure. And what did we say that would be? 2 prop Z test. We did 2 prop Z int to do the confidence interval. We'll do 2 prop Z test to do a hypothesis test. Step number 4 is to compute the test statistic, which is a Z, and the p-value. Z is computed by taking the difference in the point estimate minus the hypothesized value divided by the standard error. But I will warn you, the standard error is different for a hypothesis test than it is for a confidence interval. This is it for a confidence interval. But remember we had the same difference when we did 1-sample problems? When we do confidence intervals, we plug the p hat in there because we didn't know what p was. But when we do hypothesis tests, we're hypothesizing what p is, so then we can use that value. So for 1-sample problem, we put in p sub 0, the null hypothesis. Well here, I don't have values that I can plug in for P1 and P2 from my null hypothesis. right? This doesn't tell me what P1 and P2 are, it just says they're the same. So I still don't have values I can plug in there, but if I hypothesize they are the same, the two groups have the same proportion, then my best estimate of that proportion is to pool the two groups together and get what's called the pooled estimate. And that pooled estimate is labeled P hat with no subscript. And it's computed by adding together the two samples. So add the two number of successes and add the two sample sizes, do the division, and you get P hat. And then you plug P hat in both places. P hat, 1 minus P hat, P hat, 1 minus P hat, and then divide by their two sample sizes. Right? So if I probably won't on the test ask you for the standard error from a hypothesis test. If I ask you a standard error, it'll be from a confidence interval. So this will be the formula. But I can't say for sure what they're going to do on the online homework. They may say, what is the standard error for this hypothesis test? Then you know you need that P hat with no subscript, which I'll show you in a minute. Your calculator does give you that automatically. Okay, so let's get these straight out of the calculator. So go back to your stat button, and then test, and then down to 2 prop Z test. And the data that you entered before should still be there. So now you just have to pick the correct alternative and then hit calculate. And the correct alternative, we're doing the not equal symbol. So we have P1 not equal to P2. So make sure that one is the one that's selected. And press calculate. And what it gives me is Z equal 5.319. Now, what is a Z test statistic again? Number of what? Number of standard errors that the sample difference was from the hypothesized difference of 0. Right? Well, that's 5.3 standard errors away. Is that a lot or is that a little? That's a lot. So I expect to get what kind of a p-value? Really small, because I'm way out in the tail. Right? Marianne?
What did you say Z is again?
Number of standard errors away from the null. Okay? So the p-value is also given there. Now, when you look at this, it gets a little confusing because there's 4 lines that have p's in them. So you just have to learn to read it. The first one is p with no hat on it and no subscript. That is the p-value. So the p-value is 1.0459 times 10 to the negative 7, which is 0.0000001046. A really small p-value. So what do really small p-values tell you to do? Reject the null hypothesis. When in doubt, make a confidence interval. If you can't remember, you forgot to make out your cheat sheet or whatever, you come in, I can't remember it. I can't remember what a p-value is. Is it small p-values I reject or is it big p-values I reject? Do the confidence interval. Your conclusion on the hypothesis test has to be the same. We've already done the confidence interval, and it says 0 is not plausible. That says reject the null hypothesis. So small p-values tell you to reject the null hypothesis. So step number 5 is conclusions. I won't take the time to write it because I'm out of time, but let's say it in words. What's the conclusion?
We have sufficient evidence that
Talk about smokers and talk about exercise.
the difference between smokers who exercise and non-smokers who exercise is not 0?
It's not, and that would get you full credit. We have sufficient evidence, here's a little bit simpler way to say it, that the proportion of exercisers among smokers is not the same as it is among non-smokers. I might have said non-smokers both times, but you get that. All right? Okay, you've got a homework set due tonight. 10.1 will be due Friday night. On Friday in class, we will do our review session. So come with your review sheet filled out.
What are you gonna have the answer?